Welcome back, everyone. Today we come together to talk about section 1.6, which is the integrating factor. Now, I'm going to start off the lesson by trying to motivate why we care about the integrating factor, and it goes a little bit like this. Let's start off with something simple and obvious, something that you've done before. If you were to be told that y prime equals x to the fourth and asked to find the the function that solves this differential equation, you would know to integrate both sides, and you'd get 1/5 x to the fifth plus c. Now, if we make the left-hand side a little bit more complicated, okay, and we said it's the derivative of x cubed y that's equal to x to the fourth, how would you solve that? Well, you would integrate both sides. You'd be left with x cubed y equals 1/5 x to the fifth plus c, and then divide by x cubed, and you would have your solution. Complicating that slightly, we can say the left-hand side is x cubed y prime plus 3x squared y. That is the derivative of x cubed y using the product rule. And said, let's solve this differential equation. Now, it would be incumbent upon you to look at the left-hand side and say, that looks like the derivative using the product rule of something. What would that something be? Oh, aha, it's x cubed y. And then integrate both sides, and you've already seen the rest of that. Take this one more step. Start with this thing that we somehow saw that was the derivative of x cubed y, and we integrated both sides and said, let's instead take this and divide by x cubed through each and every term. So you'd be left with y prime plus 3 over x times y equals x. And that is not at all obvious how to solve that differential equation, even though we know that if we were to multiply by x cubed through each and every term, then the left-hand side would be the derivative of some product, and then we could integrate both sides once we figured out what that product was, and so on and so forth. Okay, so our goal is to find this magic factor that you multiply through each and every term to solve a linear differential equation. Okay, so this term that I said that was this magic factor that you were to multiply by each and every term to solve the differential equation is called the integrating factor. And the integrating factor for the problem that we've been working with is x cubed, because when you multiply both sides by that factor, it allows you to write one side as the derivative of a product, and then integrate both the left and right hand sides. So the question that we need to answer is, how do you find out what that special integrating factor is that you can multiply both sides to make work? Okay, so I'm going to go through a proof. I called it an unnecessary proof, but I want to make sure that you know that this is not just make-believe stuff. I'm only saying it's unnecessary because I'm not going to ask you to prove it. So here we go. We start with a differential equation that's of the form y prime plus some function of x, y equals q of x. Okay, just to give you an advance warning, the q of x is irrelevant. It doesn't matter what this side is right now. The thing that we multiply by, the integrating factor, is independent of the right-hand side of the equation. It just, in the end, gets multiplied by it, but really the p of x is the thing that we want to pay special close attention to. So here we go. We multiply by this unknown factor that we're going to call I of x. So I multiply y prime by I of x, I multiply this by I of x, I multiply that by I of x, and I'm left with something like this. Now, for this all to work out, what's underlined here needs to be the derivative of some product. What is that product going to be? Well, because you have y and y prime here, one of the elements of the product has to be y. Because remember how the product rule goes. Okay, it's the derivative of the first times the second plus the derivative of the second times the first, or vice versa. Okay, well, one of those elements in the product has to be y, and the other one has to be y prime for this to be the derivative of a product. It's the other thing that we don't know what it is, so let's call it something else. Let's call it f of x. Okay, so if you take the derivative of y times f of x, you get I of x. Oh, sorry. If we take the derivative of y times f of x, we get y prime f of x plus f prime times y. Okay, that's the derivative of the first times the second plus the derivative of the second times the first. Okay, but we also know, because the derivative of y times f of x is replacing the left-hand side here, it's equal to the left-hand side. So we have a is equal to b and a is equal to c, so c is equal to b. Okay, so that's the transitive property of equality. So we know that y prime times f of x plus f prime of x times y is equal to I of x times y prime plus I of x p of x times y. If you matched up term by term, okay, y prime times f of x has to be equal to y prime times I of x. So what does that tell you? I of x and f of x are the same. It also tells you that f prime of x is the same as I of x times p of x. Okay, because they are the thing that's multiplying by y. So if I take this equation, f of x equals I of x, and I take the derivative of both sides, you get f prime of x is I prime of x, but you know that f prime of x is I of x times p of x, so that means I of x p of x is the same as I prime. Okay, and if you were to divide both sides by I of x, you get I prime over I is equal to p of x. Okay, and at this point, if you were to integrate both sides, the left-hand side would be the natural log of the absolute value of I of x. Okay, because the derivative of the bottom is in the top. So this is a natural log integral, which means that the natural log of the absolute value of I of x is the integral of p of x, and if we exponentiated both sides, what we would retrieve is the integrating factor I of x, the magical thing that we're supposed to multiply both sides of the equation by, is equal to e raised to the integral of p of x. Okay, so I kind of wrote these notes that, told you how to solve the differential equation if you take into consideration the left-hand side. But you can ignore all of this, or you can look at it. It doesn't really make a difference, because you're not going to memorize that formula. I would strongly encourage you not to, and just carry out this process. Okay, simply put, what you're going to do is you're going to compute e to the integral of p of x dx. Now, taking you all the way back to this page, okay, this technique only applies to differential equations that are of this form. So the coefficient on y prime is 1. Okay, you have some function of x times y, and everything on the other side of the equal sign is involving x and only x. Okay, so you can't use this technique when these conditions are not satisfied. All right, so now getting back to the four-step process. You compute the integrating factor, multiply both sides by the integrating factor. Step 3, write the left-hand side as the result of the product rule. Now, it's guaranteed to work if you did step 1 and 2 correctly. The left-hand side will be the derivative of some product. If it's not, you made an error in step 1 or 2. Okay? And then step 4 is to integrate both sides of the differential equation, and then you'll solve for y. Okay? So, we have 4 examples. Let's take a look at them. First off, use the integrating factor to solve the problem that we just did. Okay? So we know the solution to this. It's on the first page of our notes. Okay, but let's pretend that we didn't know that, and we'd take the steps to find it. All right, so y prime plus 3 over x times y equals x. So in this case, my p of x is 3 over x. My q of x doesn't matter, but my q of x would be x. And I'm of the right form. Okay, this y prime has a coefficient of 1. This is a function of x. This is a function of x. Okay. Our goal is to write the left-hand side of this as the derivative of some product. To know what I need to multiply by to make the left-hand side the derivative of some product, I look at e to the integral of p of x. Okay, so what is that? Okay, it's e to the integral of 3 over x dx, okay, which is e to the 3 times the natural log of the absolute value of x, which is e to the natural log of the absolute value of x cubed, okay, which is x cubed. Okay, here I use properties of exponents to write that inside the logarithm. Now, yes, I missed a plus c. Yes, I'm not talking about the absolute value bars. Okay, there is an explanation. You can read it in the book why you're not going to use the plus c, why you're not going to use the absolute value bars. I'm going to leave it out of the lecture, and I'm just going to say this is what you do. Okay, so now we know that the integrating factor for this problem is x cubed. So I'm going to multiply this side of the equation by x cubed. I'm going to multiply this side of the equation by x cubed. So what you end up getting is x cubed y prime plus 3x squared y equals x to the 4th. And because I did everything correctly in step 1, okay, I know that the left-hand side is the derivative of some product. Okay, now what is that product? Well, it's got to be y times something, because I have y prime here and y there, so I know one of the terms in this summation is going to be y, and the other one's going to be the derivative of y prime, the derivative of y, which is y prime. I kind of said that awkwardly. Here, let me write this down. The product rule says the derivative of f times g is f prime g plus g prime f. Okay, so it doesn't matter which one you pick, okay? The derivative of f is going to be present and f is going to be present. So that means y would be acting as f, y prime would be acting as f prime. Well, what would be acting as g? Well, the answer is x cubed, because 3x squared is my g prime. So I have f prime g plus g prime f. F prime g plus g prime f. There you go. Okay, the left-hand side is the derivative of this product. One of the elements in the product will always be y. Okay, doesn't matter how many times you do this technique, it will always be y. It's finding out what this is that is I don't even say complicated, it's the other element to this step. And that is going to be equal to x to the fourth, at which point I integrate both sides with respect to x. Okay, so I'm taking the integral with respect to x of the derivative with respect to x. So that leaves me with y times x cubed. Okay, this is 1/5 x to the fifth plus c. Here your plus c is important, okay? I know I pick up a plus c from each sides of the integral, okay? I'm just gonna put it on the other side, okay, the right-hand side. And now we divide by x cubed. So that's 1/5 x squared plus c over x cubed. Okay, and there's your answer. All right, so that's how the process works. Okay, let's try a new problem. Find the general solution to dy dx plus 2x over 1 minus x squared times y equals 4x. So here, the integrating factor I of x is going to be e to the integral of, okay, well, first off, this is y prime plus this is my f of x times y. Oh, I'm calling it p of x, I think. P of x times y, and this right here is my q of x. Okay, so I'm of the right format. P of x is 2x over 1 minus x squared dx. All right, so let's take a look at that first. 2x over 1 minus x squared. The derivative of the bottom is minus 2x. I have a 2x on top, so I'm off by a negative. Because the derivative of the bottom is almost in the top, I'm looking at a natural log type integral. So you're looking at negative the natural log of the absolute value of 1 minus x squared. You're going to insert the negative into the logarithm. So now that's 1 over 1 minus x squared. And that's your integrating factor. So you're going to take y prime plus 2x over 1 minus x squared y. I'm recopying the problem right now. And you're going to multiply it by, sorry, got one step ahead of myself. The integrating factor is e to this integral. So now I would apply e here and e here. The e's and the natural log would kill each other off, and my integrating factor is 1 over 1 minus x squared. Okay, so sorry I got a little bit ahead of myself. This is 1 over 1 minus x squared on the right side. On the left side, this is 1 over 1 minus x squared. So we distribute. We get 1 over 1 minus x squared, y prime, plus 2x divided by, now I have 1 minus x squared times itself. So that's 1 minus x squared all squared times y equals 4x over 1 minus x squared. Get rid of this so you guys can just not be distracted by that. Okay, so at this point, I know that if I did everything right, the left-hand side is the derivative of a product. One of those elements of the product has to be y. Okay, what's the other one? Okay, is it 2x over 1 minus x squared all squared, or is it 1 over 1 minus x squared? The answer is it's 1 over 1 minus x squared. Okay, how did I know that? Well, a couple different reasons. Okay, if this is f prime, then this is g. This is g prime, this is f, so there's f right there, g is right there, 1 over 1 minus x squared. If you're at all uncertain, okay, just double check. Take the derivative of 1 over 1 minus x squared. Obviously, I'm not going to use the quotient rule. Oops. So I would rather use the chain rule. Write this as 1 minus x squared to the negative 1. Bring the negative down. 1 minus x squared to the negative 2 times the derivative of the inside, which is negative 2x. The negatives cancel. We're left with 2x and 1 minus x squared. So that's that term right there. Okay. So we now have written the left-hand side as the derivative of some product, okay, and that is equal to 4x over 1 minus x squared. So now we integrate both sides with respect to x. Okay, on the left-hand side, love this step, it's the easiest one. Y times 1 over 1 minus x squared. On the right-hand side, okay, it's kind of similar to what this was right here. This is 4x over 1 minus x squared. This is 2x over 1 minus x squared. So we're going to get the same answer, just multiplied by 2, because this integrand is twice as large as that integrand. So I don't even have to do the work over again. So that's really neat. I get this to be negative 2 natural log absolute value of 1 minus x squared plus c. Very nice. So at this point, my goal here, let's see, we have a negative 2. We can throw that inside the natural log if we are so inclined. Otherwise, we can multiply both sides by 1 minus x squared. Okay, and what do we get? We get y equals negative 2 times 1 minus x squared times the natural log of the absolute value of 1 minus x squared plus c times 1 minus x squared. There you go. First order linear differential equation. There's your general solution. And we have an answer. Not the produced of answers, of course, but an answer nonetheless. All right. Example number 3. Y minus e to the x times dx plus dy is 0. Its initial value problem, its initial condition is y of 0 is 1. Okay, let's see what we can get. Now, first off, this is not of the right form. Okay, we need it to be y prime plus or minus f of x times y. I keep calling it f of x. It's p of x times y equals q of x. So, how do we resolve that? Well, let's divide every term by dx. Okay, so what am I left with? I'm left with y minus e to the x plus dy dx equals 0. Now, writing this in the correct format, okay, we want y prime to lead off this plus y equals e to the x. So I'm going to add e to the x to both sides. Leave the y on this side. And there you go. So now I'm of the form y prime plus p of x times y equals q of x. This is my q of x. What is my p of x? My p of x is the function 1. So the e raised to the integral of p of x is equal to e to the integral of 1 dx, which is e to the x. So that's my integrating factor. I'm going to multiply both sides of this differential equation by e to the x. And see what I get. I get e to the x y prime plus e to the x times y equals e to the x squared, or e to the 2x, depending on how you want to look at it. So as promised, the left-hand side is the derivative of some product. It's y times e to the x. And you can always, and should always check your answer. So the derivative of y is y prime times e to the x plus the derivative of e to the x, which is e to the x times y, equals e to the 2x. Let's integrate both sides with respect to x. And let's see what we get. We get y e to the x on the left. We get 1/2 e to the 2x plus constant on the right. Does that look right? Yep. And now let's divide by e to the x. And let's divide by e to the x. Okay, so there's summation in the numerator. So when I divide by e to the x on the right, I'm going to have to divide both terms. So that's going to be 1/2 e to the 2x divided by e to the x is e to the x plus c divided by e to the x. Well, that's c times e to the negative x, because again, the exponent is in the denominator. And so just to make it perfectly clear, what I'm doing is I'm looking at this, I'm splitting up the fraction into its two parts and simplifying each term. And that's all equal to y. So y equals 1/2 e to the x plus c e to the minus x. And that's my general solution. But they didn't want a general solution. They wanted a particular solution. So what was the initial condition? Y of 0 is 1. So 1 equals 1/2 e to the 0 plus constant e to the 0, well, the negative 0. There you go. So 1/2 plus c, so c is 1/2. So our solution here is 1/2 e to the x plus 1/2 e to the minus x. There's your particular solution. All right. Let's put that there. Last problem I wanted to look at was example number 4. Y prime equals the sine of x times y secant x minus 2. So, hopefully what I've done is I've increased in degree of difficulty. I'm not saying this one's going to be difficult, but there's going to be more steps involved in putting it into the right format than in example 2 or 3. So what's the right format? Y prime equals y times the sine of x times the secant of x. Well, secant of x is 1 over cosine x. Minus 2 times what? Minus 2 sine x. Does that look right? Yes. It's one of the bad things about lecturing on video. I don't have anybody to stop me and point out when I make a mistake. Y prime tangent x, or y prime equals y tangent x, minus 2 sine x. Now, I need this on the side of the equation with the y prime. So this is y prime minus the tangent of x, y, equals minus 2 times the sine of x. Now what happens? Well, we have an integration problem. We need to know our integrating factor. So our I of x is going to be e raised to the integral of minus tan x dx. Okay, so what's the integral of tangent? Okay, I might need a scratch paper for my scratch paper. The integral of tangent x is the integral of sine x over cosine x. And if you look at this integral right here, the derivative of the bottom is almost in the top. The derivative of cosine is negative sine, so I'm off by a negative, but fortunately, this problem, they gave me a negative, so I can put the negative sine x right here. And now what do I have? The derivative of cosine x is negative sine x, so this is the natural log of the absolute value of cosine x. All right. So this is e to the natural log of the absolute value of cosine x. So we get e and the natural log cancel out, the absolute value bars. Like I said, we won't go into the description of the book describes why the absolute value bars aren't necessary. So this is equal to the cosine of x, and that's my integrating factor. So we multiply both sides by the cosine of x, by the cosine of x, and that's y prime cosine x minus tangent times cosine x. So that would be what? Sine x over cosine x times cosine x. So tangent is sine over cosine multiplied by cosine times y, and that equals minus 2 sine x cosine x. So the cosines cancel. We get y prime cosine x minus the sine of x times y equals minus 2 sine x cosine x. Just simplifying as we go. The left-hand side is the derivative of some product. What is that product? It's y and cosine x. You can confirm that. The derivative of y is y prime times cosine x plus the derivative of cosine x, which is minus sine x, times y. That's equal to minus 2 sine x cosine x. Integrate both sides with respect to x. You get y cosine x. On the left-hand side, you get what? Negative 2 sine squared of x plus c. Okay, so if you're wondering how he came up with that, I noticed that the derivative of sine is cosine. So I'm looking at this as sine to the first power, and I'm thinking, what would I take the derivative of using the chain rule? that gave me the 2 sine x cosine x, where cosine x is acting as the derivative of sine? And the answer is sine squared of x. So you look at this as sine of x all squared. Okay. In fact, I think I made a mistake. Don't need that 2 out in front. So if I take the derivative of sine of x squared times the -1, the 2 comes down, that gives me -2 times sine of x all raised to the first power times the derivative of the inside, which is cosine x, and that's -2 sine x cosine x, which is what I wanted right there. All right. It's a good thing I checked that. So divide both sides by cosine x. You get minus sine squared of x over cosine x plus c times, let's call it the secant of x, because I'm dividing by cosine. And I'm only going to simplify that if it makes sense to simplify it. So pulling back my scratch piece of paper, sine squared of x is sine x over cosine x. So that's going to be tangent of x, sine x, and tan x sine x is no better than minus sine squared of x. All right, so we'll leave our answer like that. I can't promise you that there's not a nicer way of writing that, but each way that you can come up with is going to be equivalent. All right. Now, you can always check your answer in each one of these. Okay, so I should be able to take y here, plug it right back in. I'm sorry, I don't know if I'm pointing on the screen. I should be able to take my solution that I just boxed and be able to plug it right back into the differential equation and get a true statement. If not, I made a mistake. Okay, entirely possible, especially when you're integrating, you can miss a negative or something along those lines. Okay, so just be careful when you're working through this. Hopefully I didn't make any mistakes going through this. But if not, I'm sure you'll let me know. Okay, have a good evening. Take care.